You might have seen Jetsons, and I just found out recently that Jetsons are very, they seem realistic today, because you can see flat screen. It's 1962, you see flat screen, you see smartwatch, you see video chats, you have drones, you have commercial space flights, which is kind of trendy topic right now, right? You have Roomba. It's really like, my God, it's 55 years ago, and they all knew it's going to happen. But one thing that didn't happen yet is Rosie. So Rosie is a servant, like robotic servant, so everybody would like to have a servant right at home. We still don't have that, and there is a couple of reasons why. So again, I'm Maciej. I work for Nomagic, and we are trying to push forward the current capabilities of robots so that we one day, like, I don't know, maybe 10 years from now, we actually can have Rosie at home doing things for us so that we can get laid. So today the robots look like this. They work, for example, for a BMW. They basically put together a car, and they're very good at that. They're pretty fast. They're extremely accurate, extremely precise. But all they know about the world is the way they were programmed. So they were programmed to do specific moves, and these moves are repeated over and over again. These robots are extremely expensive. We speak about hundreds of thousands of dollars for a robot, and then hundreds of thousands of dollars for programming the robot and for integrating in a factory. So that's why basically it's not manageable for households. Also, the fact that they are pre-programmed means that they are useless at home. You can't pre-program a robot to make dishes for you, right? It's just not going to happen. But once we need to do a couple of things. We need to make robots that are cheaper. And we have now cheaper robots. You can buy a robot for like 35,000 euro, which is like a magnitude, order of magnitude lower than the robots at factories. And we can add vision to the robot. And if we use deep learning, then we might actually get some generalization that will help us train the robot on one set of tasks, and hopefully it will work in some real-world situation. But we are far from this. We are pretty far from this. You will see very, very, very soon. And yet, there is a number of companies, a number of research centers that are actually trying to make it a reality. So you can see here, so I will focus during this talk on grasping and picking, because it seems that it's like the first obstacle that we need to overcome. If we know how to pick objects, how to grasp them, then we will need some other steps to do. We'll need to know how to move them, what to do with them to actually succeed in any task. So here you see a two-finger gripper that grasps like that. So it's nothing like a hand, it's only two fingers, which arguably is oversimplification. You can't probably do a lot with two-finger gripper, but let's start somewhere, right? And something you may not see is here is a suction gripper, but you can see the suction gripper in action on the next slide, probably, if it's going to work. Oh. What? Okay. You can see it here. So this is actually a robot deployed in a warehouse by our company. So this is a suction gripper. So it basically uses suction, like in vacuum cleaners. It's pretty much the same story as a vacuum cleaner. And the task that we want to tackle, and many other groups want to tackle, is basically a situation where you have a pile of objects, and it can be pretty much anything. Here, well, it's not representative because you can see that most of the objects are like boxes or something like that, but in reality, there are also objects that are not boxes, and we still need to be able to pick them and do this stuff. So in our case, it's like putting it on a conveyor belt here. So the object then gets shipped. Once we put it into the box, it gets shipped to a client. So if you one day when you buy in an online shop, like you will be 100% sure that it was packed by a machine and not by a human. So this task right now is done by a bunch of people who actually doing this repetitive task of putting objects into a box. And you can approach this problem like any real problem. You can approach in many different ways. I will show a couple. This is by far not exhaustive, but these seem to be the most important at the moment. So first thing you can do is you can try to do some kind of supervised learning. And the easiest thing you can do, you can take a, how does the laser work? Okay, you can take a picture of items and you can simply label it where you can stack, or in this case, a picture of items and where you can grasp it, how you should grasp it. There is a basic problem with this. So as long as you can see the object clearly, then the labeler can actually do a decent job in labeling it. But once you have, like I showed you before, like once you have like 100 objects, and you don't know the objects because you have never seen them before, then even for human, it's not exactly clear sometimes how to label it. So is it a good place to grasp? Is it a good place to stack or not? That's far from clear. So there is a bias. Like when we are going this way, we are incurring a bias, which is nothing like in supervised ImageNet, for example. Right? In ImageNet, you may be wrong, but typically you are not biased. Here, you will be biased. So this is an approach from Amazon Picking Challenge, actually, one that won the thing. And the reason it won, because it was very fast. And they were able to change the gripper from two-finger gripper to section gripper, and it turned out that it's a really useful strategy. And it's very simple as well. There is nothing really going on. You have RGB image, you have depth image, you simply have a fully connected network. You somehow combine those two channels of information, and you simply have a semantic segmentation. So this semantic segmentation tells you where you should grasp and where you shouldn't grasp. Yeah, so the good thing about it is super simple. You don't need to do anything with a robot until you actually test it. During testing, you actually want to see that the robot actually does the right thing. But during training, you can simply gather lots of pictures, have them labeled by someone, and you are done. A similar approach, somewhat more involved, is to instead of doing semantic segmentation like here, you may want to do some kind of you may want to use some kind of faster RCNN or RCNN-like approach where you want to have some region of interest and have the network focus on some part of the image so that the prediction is actually better. And this is something that was done just this year by a group. Similarly, yeah. So, like I said, so one of the problems is the bias of human labeling here. The other is that obviously this is very task specific. So we are talking here only about picking. There is a high chance that if the diversity of the objects in training is not big enough, then at some point we'll find objects that we can't really tackle. And we'll need to retrain our network, which, well, it's not that big deal. But the biggest problem from kind of production perspective is that you need to calibrate a lot of things, because you need to, once you know on the picture what you want to grasp, you still need to know how to make robot to go there. And these are two different frames of references. You need to calibrate them so that you actually understand where to go. So ideally, you would like the robot to just know, because programming this, believe me, is a pain in the ass. Yeah, so there is a bunch of other papers that go in this direction. There is So this one I mentioned, this one I mentioned. So this one does a similar thing, but they are using the YOLO approach. So they are trying to, to say in like every tiny piece of the image whether this will be a good grasping position and where exactly in this piece of image it will be. So once you decide that you don't want to calibrate anything, you go the unsupervised way. And this is a paper from 2 years ago that was really somewhat a breakthrough, I would say. So you basically have a farm of robots that at first they just do random things. They have limited they can do some limited set of moves so that we know that ultimately they will find the object and they will grasp it. But other than that, they start with very low accuracy, like 10%, maybe 20% by pure chance. But then we use this data to train a network, and then we run again this farm of robots on these trained networks, keeping our fingers crossed that this time it's actually going to work a little bit better, and that's actually what's happening. So they had a DeepMind 14 robots, and so a total of 28 months of experience was gathered during this experiment, and they were using RGB cameras. So the nice thing about it is that they put the RGB cameras roughly so they didn't need to calibrate it. So each camera was pointing toward this cart, but like what was exactly the position, the pose of the camera, that didn't much matter, which is awesome. I would love to have that. Like my biggest, let me show it to you again. So. Right, now you see the normal speed. It's not really fast. And now you see 5 times faster. So it's basically 5 times too slow to be useful for anything. And there is a couple of reasons for that, but the basic reason is I would say that they are doing, like at each step, like every, I don't know, 100 milliseconds, they are doing a new prediction, and they need to wait for the new prediction to come. So, and they do it sequentially. Maybe if they did it in a smarter way, it would actually work. So roughly, what they are doing is like I said, they keep moving down, they keep improving on their prediction. The camera does not move, but in the camera you start seeing the gripper, and that's why once you see the gripper in the camera, it's like a feedback loop, and you can see that, oh, so I wanted to go here, but now that I see the gripper in the camera, I should actually go like 2 centimeters to the left. And network-wise, what's going on is that you're feeding it with the image before the gripper was seen, like the time 0, and then the current image, possibly with the gripper, like here. You feed it in the network, and you feed also what kind of how should I rotate the gripper to make it successful. And basically, you need to run it like, I don't know, maybe 64, maybe 128 proposals, and this network decides whether this proposal is a good proposal or not really good proposal. So that's one of the reasons why it's pretty slow. Like, I didn't see too much effort into trying to improve on that. There was some, but I think if someone thinks about buying 14 robots, that's a stopper for universities and many places, because they are not cheap. The fact that they're a little bit smaller than what you saw before does not mean it's cheap. It's pretty much the same price. So the problem with this unsupervised approach, so again, it's task-specific, but on the other hand, you barely have any programming, and the programming is very generic. You do it once, and you have different tasks. You are basically done. You don't need any calibration, which is super cool. It's pretty slow, and it's data inefficient. It needed 28 months. It was 800,000 images. If you think about ImageNet, it's not too much, but if you think in terms of robots, like each each proposal, each image in the data set, it takes probably like 2-3 seconds to generate, so it's a lot of time. Plus, you need human supervision during training because someone needs to refill these cards with new items. And so you basically, it's not too much fun if you need to do it all the time. So like I said, I didn't see too much effort into improving this direction. There was actually one paper from this year by the same group, and they used instead of this open loop sort of approach, they used reinforcement learning. So I complained about the fact that the human had to interact all the time during training. So there is this super interesting paper from a year ago by OpenAI where they applied, where they decided we want to train everything in simulation and we want to transfer it to real world. Now, there is a lot of problems with that. There was a lot of problems with that before this paper because basically, well, it's pretty understandable. If you keep training in a world like that, it's not going to generalize to a real world. There is no chance. So what they came up with is, okay, so we're going to generate like millions of different worlds, and there are some things that are identical in this world. So you always have this table, you always have a robot, you always have some items on the table. But the textures, the lighting, the colors, all of that is pretty much randomized. And funnily enough, it actually works. I wonder how big surprise it was for the OpenAI team, but it actually works. Again, it's not too fast, but the bigger problem is that the precision of the grasp is not like super cool. So the average precision is 3 centimeters. I mean, it's super cool that it works anyway, but it's not production ready in any way. So 2 more words about that. So it was interesting that so you have here a graph of accuracy, average error in centimeters, depending whether the network was pre-trained or it was not pre-trained or not pre-trained. So you can see that after some thousands of images, it really does not matter whether the network was pre-trained or not, suggesting that like the generalization was pretty much the same, no matter whether you started from scratch or not. On the other hand, what really mattered is how many unique textures you were using. So how much randomized your environment was. The more randomization, the better the results. And this is a newer thing. This is not about picking, but it's super cool. In some sense, it is about picking. So in OpenAI, they pushed forward, and they bought a robotic hand. It's only $100,000 one, and it breaks like every hour, they say. So what they did exactly the same thing. So they trained in simulation. They trained this hand to do a task, which is it needs to roll this cube with letters, and they give the hand a goal. So how should the cube look like after when it's successful? And it needs to roll it with one hand, this cube. I don't have a video for you, unfortunately, but it's super cool to see that you can actually do it purely in simulation. And one trick to make it work was that instead of only randomizing the colors, textures, etc., they had to randomize some physical properties of the hand, like friction between the cube and the fingers. Right, so again, with simulation, the biggest problem is that the reality gap, well, we can overcome it, but we lose on precision, and there is no, at the current moment, currently there's no really good solution to that. And you need to do a lot of programming in simulation. You need to basically create a whole simulation, recreate a whole hand in simulation. It's a lot of fun, but and once you have it, you can easily parallelize your training on as many computers you want, which is super cool because computers seem to be cheaper than robots. But it doesn't seem to be ready for production. We can't just train something and use it because of the reality gap. On the other hand, maybe because it was so much easier to train in simulation, there is a number of papers that are doing interesting things in this field. For example, there are some proposals to make the simulated world look more like real world by using some GANs. There are also a number of papers where the problem with precision is even bigger than I mentioned. So, for example, this paper they have super cool values in super cool performance in simulation, but when they transfer it to real world, it drops by 5 times or something like that. So it's not that easy. But arguably, like the thing that you would really want to do, like the thing that would be super cool to have is to teach a robot by demonstrations, because demonstration is cheap. I can show you how to move an object, and you will, like, everybody would understand what I want to do. I want to, I don't know, like take this and put it here. If there was a box and I said, hey, I want to grab this thing and put it in the box, it's clear what I want to do. I don't need to explain it to you, right? And there is a number of papers that actually go this way. This is notably by Chelsea Finn, one-shot imitation from observing humans. So what they're doing is they're using meta-learning to actually perform that, meta-learning and some other tricks and stuff. But like the task of the robot is to recreate the pose that was done by human. And interestingly, the robot, when presented with the trajectory done by human, tries to also mimic the moves the human did with its own hands. So the trick here, for example, they had this task of placing targets. So they have a number of things, and they were putting into a bowl. And then they had, in the test set, they had other things and other bowls, and yet it was able to grasp the concept that we don't want to put this thing into this bowl, but we want to put something into a bowl. And they used here this meta-learning. This is, I believe, a super cool thing, like this meta-agnostic meta-learning that was proposed last year by Chelsea Finn. There is a bunch of effort to make it more robust. But basically, like, meta-learning is a way to learn how to quickly adapt to a new task that is sort of similar to what we had before, but not the same. So again, learning by demonstration is super cool, and I believe this is a thing that will be super important in like 1-2 years. But it's, oh, sorry, this actually was not the right slide. Okay, let's skip it. Sorry. So what I wanted to say is that learning by demonstration is super cool, but there is a number of things that does not work. One of them is sometimes the task has an inherent ambiguity. So, for example, do I want to move this object here, or do I want these two objects to be in the same distance? It's not clear from a single demonstration. So sometimes single demonstration is not enough, and the algorithms should be robust against it. And there is, again, effort from, I just saw on NeurIPS, 2 approaches of how to improve on MAML to actually, so that this meta-learning can actually provide you with 2 answers or 3 answers if you need to. When it's confused, it can show you, okay, do you want this or do you want this? Super cool. So challenges ahead, like robots, I would say nearest challenges that we should tackle is first of all maximize speed. Well, so I'm saying this from like production perspective, where we once we pick the object, once we pick the product, and we move with it, we want to go as fast as possible, but not faster, because if you go faster, we're going to lose the item, and that's a big problem. How to move as fast as possible without dropping the item? Maybe again we should use vision to actually track what's going on with the object, and if it starts wobble, then maybe we should just not go as fast, right? And something like the trade-off between the maximum speed is firm grasp. So we sort of don't know yet. So we have vision, but normally if you grasp something, you kind of feel how firmly you grasped it. We don't have it with robot, with suction gripper. Even worse, we don't have it with two-finger gripper. But there is like more and more proposals of how to create a tactile sensor, a small tactile sensor on the two-finger gripper, so that you can actually feel the object. So hopefully, at some point, we'll be able to actually feel with these two fingers that, oh, this object is actually slipping away, and act on it. But by far the most interesting is data efficiency. So we know that supervised learning is not extremely data efficient, but reinforcement learning is extremely data inefficient. And as much as there is a lot of work toward like reducing this data inefficiency, there is still so much to do if we want to apply it to robots, because robots need to pick a concept as fast as we do, as humans do. Otherwise, it's not going to work. Maybe we need to spend like 1 year as a child, like a newborn does, spend 1 year to develop a certain skills, so that later we are very fast in doing other stuff. But we are not there yet. And last but not least, collaborative robots. If you want to put a robot at home, we want to be pretty sure that it's not going to kill us. So there is this concept in the industry which is called collaborative robots, and we have actually a collaborative robot in our office, but the running joke is that the collaborativeness ends when it kills you, because basically it will stop. When it hits you, it will stop. But if it hits you and kills you, it's too late already, right? So they are moving very fast. They can move very fast, and there is a big lag between the moment it realizes, oh, I should stop, and the moment it actually stops, like 1 second. So you're smashed at this point. Yeah, that's it from me. Do you have questions?